Hello everyone, welcome back to the latest lecture session. I believe we have been discussing equilibrium between the three phases, air, water and soil. But in that context, I believe we were, or as of now or until now, we have been only looking at air and water interactions or the equilibrium between these two phases. And in that context, we looked at some basics with respect to the equilibrium constant, right, and also with respect to the acid dissociation constant, right. And why acid dissociation constant? Because acids and bases, they play a remarkable role in our everyday life and certainly with respect to different life forms too, right. And in that context, we were looking at an example. So let's continue with that example. And where is the example here? Okay, so here we are going to have to calculate the pH of a water droplet. The key aspect is we are assuming that it's reaching equilibrium with carbon dioxide, and the other assumption, which is typically not a good assumption, is that there are no other species other than carbonate species in the water, okay, but just makes life simpler or easier. So, and the concentration of carbon dioxide in the atmosphere is given as ppm by mole basis, I guess, right. So, that is something that we have out here. So, how do we go about calculating it? So, first understand that the system is in equilibrium and that H plus is not what do we say, independent of the other anions or cations, right. It is in equilibrium. So, you have conjugate acids and bases. So, if you let us say disturb one of these variables, it is going to have a knock on effect on the other variables too. So, first what are the variables or unknowns here, right. So, obviously H plus and OH minus, and then obviously the carbonate species CO3 2 minus, HCO3 minus and H2CO3, right. And we know the concentration of what do we say, carbon dioxide in the gaseous phase. So, I guess how can we get that? We have what do we say, the molar ratio here, right. Again, what is it? 370 ppm, right, into 10 power minus 6, right. Number of moles of carbon dioxide to the total number of moles, let us say. So, I guess with that we can get the partial pressure of carbon dioxide, right, P total. So, here if I assume this to be 1 atmospheres, right, I guess I can get the partial pressure of carbon dioxide, right. Do we have the Henry's constant of carbon dioxide given here? Well, we do not have it, but again you can we can look that up. Typically it should have been given here, I guess, right. So, I guess that is one way to not one way. So, we can get the partial pressure of carbon dioxide here. So, we know the concentration or partial pressure of carbon dioxide in the gaseous phase, right. So, how do we move on now, right. I have 1, 2, 3, 4, 5 unknowns. So, I need 5 independent equations. So, one is with respect to the dissociation of water, H2O, water dissociation, H plus and OH minus. For this you have the equilibrium constant, or for the water dissociation constant, I guess, or the water dissociation constant 10 power minus 14, right. Again, what is this equal to? It is equal to the product of the activities of the products, right, by what is it, activity of H2O, right, and again H2O liquid, right, and here we are assuming that it is remarkably dilute systems. So, the concentration or activity of H2O is always going to be, or in this context 1. So, it is going to be equal to activity of H plus to activity of OH minus, right, and activities we approximate them by concentration. So, again we will not go into this detail again, but something out here. So, we have one equation. So, what are some of the other equations that we have? I guess we have the Henry's constant related equation KH. I think KH we say that it is equal to concentration of carbon dioxide in the aqueous phase, right, which I can also say is directly equal to H2CO3, because H2CO3 carbon dioxide in the aqueous phase will typically be in equilibrium with H2CO3, again 1 mole to 1 mole, right. So, I can say that KH is equal to the concentration of H2CO3 by the partial pressure of CO2, right. Again we have KH, or we can get KH right, and we need to see to it that the kH units are what now, molar units per atmospheres, right, because we have the partial pressure of CO2 in atmospheres here, because we are taking P total to be 1 atmospheres, and H2CO3 we obviously want molar concentrations. So, that is 2 equations now, right, 1 and 2, right. So, what else do I have? I then can then have the acid dissociation equations, I guess, right. Again, let me go through what else I wanted to present on this slide. I guess I need to erase this. The relevant species are these, which I guess we already discussed. To solve quickly, so on and so forth, you can, okay, so I understand what it is that I want to say here. Please note that the pKa1 of the carbonic acid is equal to 6.3, right, and we know that the pH pK graph looks something like this, right. This is H2CO3, H2CO3, this is HCO3 minus, and this is just CO3 2 minus. So, this is 6.3, right, and here we have nothing else, we are just having carbon dioxide dissolving into what is this, water now. So, the pH is going to be more or less near pKa or slightly less than pKa1, right, and what we can see is that at pKa1, which is around 6.3, is there any CO3 2 minus? You see that there is little to no CO3 2 minus. So, that is what I mean when I say you can neglect CO3 2 minus if you can estimate the probable pH of the solution and compare it with pKa2, right. Why is that? Since carbon dioxide is coming in contact with the solution and there are no other species other than the carbonate species, the pH of the final solution will be slightly less than pKa1. Right. For it to be a lot less than pKa1, the concentration in the gaseous phase has to be very high. So, this is not very high. So, it will have to be relatively less than, but not a lot less than 6.3. So, you see that if I am assuming that it is going to be somewhere out here, and then at this pH you see that there is not going to be any CO3 2 minus. So, you can neglect CO3 2 minus, again that is something to keep in mind, which we will look at later. Relevant equations, I guess obviously Henry's law, right, equilibrium constant for the acid base reactions, which is what I was going to present, and we also had the water dissociation constant, and I guess I skipped ahead. So, with respect to the equations, H2CO3 dissociating into H plus and the conjugate base HCO3 minus, we have Ka1, I guess 10 power minus 6.3, which is going to be equal to activity, or in this case I am going to go with H plus directly, H plus into concentration of HCO3 minus by concentration of H2CO3. So, that is one other equation, and we have another equation here, HCO3 minus is going to be in equilibrium with H plus and CO3 2 minus 2, right. So, that for that I have Ka2, right, H plus times CO3 2 minus, right, by HCO3 minus. So, if you remember, we had other equations with respect to Kw and one with respect to Kh. So, we have 1, 2, 3 and 4 equations. So, obviously, we have 4, but if you remember, we have 5 unknowns here, right. So, the fifth unknown, typically let us say in practical scenarios you measure alkalinity or you can estimate the total carbonate, but that is not what we have here. So, keep in mind that until or looking at the aspects that we discussed earlier, you will remember that we mentioned that rather the water, any water has to maintain electron neutrality, right. The equivalent concentration of the cations is equal to going to be equal to the equivalent concentration of the anions, let us say, right, charge balance. So, that is what I have here. So, the fifth one or fifth equation is going to be with respect to, or is going to be the one where we apply the charge balance, right. So, that is what we have out here. Let us see. So, you can solve this equation. Again, keep in mind that we are asking for pH here. So, you would write, I guess, all these equations and see to it that you finally have what do we say, an equation just in terms of H plus. Then you can get pH, right, minus log concentration of H plus. Again, keep in mind pH should actually be activity, but in this case we are assuming dilute systems, and so we are taking it to be the concentration of H plus, right. So, let us see go ahead and see how we calculated earlier. So, carbon dioxide gaseous and aqueous are going to be in equilibrium, and I guess here I have KH. Again the units are molar per atmosphere. So, it is the one in the aqueous phase by the one in the gaseous phase, right. So, KH, H would be the other way around, right. Just look at the units and you can get that done, and we move on according to Henry's law. This is something that we already have, right. Carbon dioxide in the aqueous phase by partial pressure of CO2 would be equal to KH. Thus, carbon dioxide in the aqueous phase is equal to so on and so forth. And I guess we also have the other equations. Carbon dioxide in aqueous phase is going to be in equilibrium with H2CO3. This is what I mentioned earlier. So, we will skip this, and the first acid dissociation here and the dissociation constant out here, and so Ka1, that is something we have or we looked at. So, what do I have here? This is from the second equation, I guess, is it? No, we are just rearranging the terms here. HCO3 minus is equal to Ka1 into concentration of carbon dioxide in the aqueous phase divided by H plus. So, again we are just trying to see to it that we just end up with what do we say, H plus. So, Ka1 you know the value 10 power minus 6.3, KH2 I guess you know that somewhere, that is given out here, and partial pressure of CO2 is something we know or you can calculate. So, I am trying to see to it that all the variables are expressed in terms of H plus and partial pressure of CO2 here. So, next aspect is with respect to HCO3 minus and CO3 2 minus. So, Ka2 is this particular values because we know that pKa2 is equal to 10.3, right. Again, so similarly we are going to apply the relevant equilibrium constant out here for this particular reaction, and you see that H plus into CO3 2 minus by HCO3 minus, that is equal to this particular value here, equilibrium constant, and rearranging the terms we end up with this value for CO3 2 minus now. But keep in mind, as we discussed earlier, you know, because of or not because of, after analyzing this pH pKa diagram, you can see that if we estimate the pH to be, or the final pH of solution to be slightly around 6.3 or less than 6.3, you can neglect this, but I guess the people here have not neglected that, but you can. So, charge balance, sum of the equivalent concentration of cations is equal to sum of equivalent concentration of the anions. The key is it is equivalent, right, equivalent. So, what do we have? We have H plus, which is the only cation among our unknowns, and we have all the anions are out here on the right hand side. So, 2 here because we are talking about equivalents, and CO3 2 minus, its charge, it has charge of minus 2, that is why we have 2 out here, right, prefix of what is it now 2. So, this is the charge balance equation. So, anyway this term we want it to be in terms of H plus, HCO3 minus we converted it into in terms of PCO2 and H plus, same case with CO3 2 minus. But as I mentioned, if you know, you can understand some chemistry, you can neglect this term in this context, and OH minus we know that OH Kw is equal to the concentration of H plus into concentration of OH minus, right. So, you can get OH minus in terms of Kw and H plus, right. So, anyway divalent ions 2 times equivalent concentration is 2 times molar concentration, that is pretty obvious. So, substituting what we what do we say have from the previous set of calculations, we have an equation that it's only in terms of H plus and PCO2, right, in atmosphere 370 ppm on mole basis. So, obviously from what is it now, partial pressure to total being in the ratio of Ni, or the molar ratio let us say, to N total, we end up with Pi or partial pressure of CO2 to be 317 to 10 power minus 6 atmospheres. So, plugging that in, we have this term, and again as I mentioned earlier, you could have neglected the CO3 2 minus, right. Again here though I guess people are looking at algebra. So, comparing first and third term on the right hand side and blah blah, third term is 600 times smaller and so on and so forth, it can be neglected. Or what we are actually doing is, if the concentration or the pH is around or less than 6.3 let us say, or slightly less than 6.3, you know, OH minus concentration is going to be relatively negligible compared to the other what do we say, cations and anions. So, you can also neglect OH minus, and again we looked at the reasoning for plausibly neglecting CO3 2 minus, right. So, that is what we have here. Again, you can look at the terms in terms of algebra too, right. And moving on, so we are just left with these terms and a quadratic equation. Again, this is pretty simple, so I am not going to go through this. So, H plus, and what is the H plus that we end up with is 10 power minus 5.6. So, the pH is 5.6. That is something that we expected, as you saw, or as we reasoned rather. The pK1 is 6.3 and the concentration of carbon dioxide is not very high, but significant enough to bring it down to near or below 6.3. So, as you see, 5.6 is pretty much what do we say, we were relatively accurate when we predicted that the final pH, when we have just carbon dioxide at a relatively low concentration, what do we say, being in equilibrium with water, will lead to a pH that is relatively less than pK1, and that is what we have out here, right. And let us see what else we want to present here. So, in general, for rainwater containing only carbon dioxide, again keep in mind this is not a great assumption. So, again we have these generic equations, but I will ask you not to mug up such equations. I am not going to ask such questions in the exam though, right. Again, if the pH here, what do we have? Find out the pH if the atmospheric CO2 concentration is doubled. Before we try to calculate that, I guess again you need to or you can rather develop a sense of how things work. So, keep in mind that pK1 is 6.3, right. pK1 is 6.3, right, 6.3. So, earlier we had the pH at 317 to 10 power minus 6 carbon dioxide concentration to be 5.6. 5.6 is what we calculated. But please note that at pH of 5.6, most of the carbon dioxide in the aqueous phase is as H2CO3 itself. Very little will be present as HCO3 minus. You can get this even from the Henderson-Hasselbalch equation, pH equal to pKa plus log, if I am not wrong, the deprotonated form by the protonated form, right. Again, you will see that most of it is as the protonated form. And so, you see that for bringing down the pH a lot from here, you need to have a lot of carbon dioxide, because only, as you can see, as to go, if you go further out to the left, most of the what is it now carbon dioxide will stay as H2CO3 itself. So, very little will dissociate. So, what I am expecting is that even though you double the concentration of carbon dioxide, the pH change is not going to be a lot. It is going to decrease, but it is not going to decrease by a lot. Why is that? Because as we go further away from the what do we say pK1, you see that most of it is going to stay undissociated or in the protonated form. So, you are not going to release H plus, which is required to bring down the pH. So, let us see what we have. So, generic calculations, I guess PCO2 twice earlier concentration, looks like this is what they end up with, and plugging it into what we saw earlier. Okay. So, looks like the pH turns out to be 5.47, and earlier I think the pH was 5.6, I guess. As you see, it is not a great decrease, and that is the reason why you see out that. So, okay, this means that rise in atmospheric CO2 concentration does not change the acidity of rainwater by a significant amount. Again, keep in mind that even if 5.6 pH rain falls consistently over, let us say pH 7 water, I guess ocean water is slightly basic and such, but now it is starting to turn acidic. You are going to, and if the ocean water does not have enough alkalinity or the acid neutralizing capacity, you are going to bring down the pH, and it does not need to change by a lot, even by, let us say, if it turns out to be 6.5 or so, I need to see what the value is. Even a slight change in pH will kill marine life, where they will become non-existent, maybe 90%. I am throwing numbers out here, but I do remember that even what do we say, change in pH by a small degree is going to affect what do we say, or disastrously affect a lot of marine life. Again, that is something to keep in mind. Let us see. I wanted to clarify that in the context of this statement. Here we are not just looking at numbers, but we need to understand the true significance of what is happening out here, right. So, you have carbon dioxide in the gaseous phase, so rainwater coming down, it is slowly but surely bringing down the ocean pH, but again ocean pH will not be directly affected by rainwater falling on oceans, but what is happening is that you have carbon dioxide in the gaseous phase, and now carbon dioxide is going to dissolve into the oceans, and typically that is how the pH is decreasing slowly but surely. I am talking about the pH of the oceans, let us say, but I guess rainfall also plays some role, right. So, let us move on, and I guess this is something a discussion that we used to have in class, right, and what is that about, what is the pH of Coke, let us say, right, or most of these colas that you have, Pepsi, Coke and so on and so forth. So, looks like for carbonated drink you have, what do we say, the what is it, the partial pressure of carbon dioxide is 5 atmospheres. So, that is remarkably high. Keep in mind that earlier I think we had 370 into 10 power minus 6 ppm. I think this was the value when the course was started, maybe in 2010 or so. Keep in mind that now we are in 2020, or maybe the course was started in 2012, I am not sure when it was started, but this was the value quite some time ago, and now the atmospheric what do we say, carbon dioxide is something around 415 or 420 and rising though. That is something to note. You see the considerable change within quite a few years, I guess, right. Again, enough of that. So, let us move on. So, I guess just to keep students interested, we were trying to ask them to calculate what the pH of the Coke would be. Again, you will plug that in and looks like, okay, now you see that the pH is considerably low, and that is the reason why typically let us say if you are concerned with your dental health, or the state of your teeth and the enamel, you do not want to, what do we say, gulp down a lot of these acidic or carbonated drinks, right. Again, or if you need to gulp them down, not gulp them down, if you like carbonated drinks, do not wait to savor the taste, because you do not want to increase the contact between this acidic Coke and your teeth, just gulp it down, I guess. That is the way to go about it if you do want to take carbonated drinks. Again, they are saying diet Coke, so I guess that is a saver out there, right. Let us move on. If carbon dioxide is the only species that affects the rainwater's acidity, its pH is going to have to be 5.6, right. And when additional species are present at appreciable levels, pH of rainwater becomes much lower than 5.6 or 5.7. That is when you have NOx, right. We will look at that later. I believe we will look at that, and then you are going to have pH come down considerably, and acid rain that leads to disastrous results wherever it is, I guess, whichever regions experience acid rain now, right. Moving on, and again, if as we saw with just carbon dioxide, bringing down the pH greatly was a considerable issue. Why? Because pKa1 is 6.3, it is almost near neutral, 6.3, okay. So, you need a lot of carbon dioxide to be able to bring down the pH, let us see. But as we see, H2SO3, H2SO4 and HNO3, most of these are strong acids. When we say strong acids, we typically, how do you explain to someone quantitatively now? You mean that their pK value is pretty low, right. I think either near 0 or almost 0, right. So, what does that mean? Whatever is present out there is always going to dissociate, that is what it means, unlike the case with respect to H2CO3. Right. That is why the major contributors are obviously those that have a very low pKa, right. So, both substances are formed in the air. Precursors to H2SO4 is SO2. This is given out from coal power plants, because you have, I think, 2 or 3% or maybe depending on the type of coal, even 4% of sulfur in coal, and when you oxidize it in your thermal power plants or such, I guess you will end up forming sulfur dioxide, and that leads to formation of, I guess, H2SO3 and H2SO4. And NO2 NOx, I guess some in coal power plants, I am talking about nitrogen, but I think mostly it is from what do we say, vehicular emissions, let us say what is it now, petrol and diesel certainly. So, concentrations of the precursors SO2 and NO2 are greatly increased, again as we just discussed, by fossil fuel combustion, right. So, effects of acid rain, again the key aspect is, the ecosystems are being battered by different ways. Certainly humans directly, ecosystems are, what is it now, shrinking. So, their what do we say, ability to act as buffers, what do we say, between life on earth and natural disasters or sudden changes is getting relatively limited. And more importantly, as we discussed or mentioned or looked at earlier, there is a symbiotic relationship between most of these biosystems or biospheres and all forms of life, including humans, and we are killing them and battering them in different ways. So, one such way to batter those ecosystems is by releasing, I guess, tons of acid rain. So, what does that lead to? Obviously acidification of surface water, and then damage. And another aspect is that you are going to have metals, let us say, which let us say have precipitated out, but at low pH or once they come in contact with relatively acidic water, you are going to what do we say, make these heavy metals more mobile, right, or you are going to have dissolution. And again, when you have dissolution, you are going to have contamination of your water now, either ground or surface water and so on and so forth, but typically not groundwater unless you have deposits in that particular area. And obviously damage to forest and vegetation. This is a case, not this is a case, this is a what do we say, remarkable case in India, especially even in our Karnataka. And I think you would have read about iron ore being mined out of Karnataka in the last what do we say, 5 or 6, 7 years, and again open cast mines typically, and that led to acid rain considerably in the surrounding areas. So, you have a double whammy, the farmers there, they can't grow crops because this particulate matter from these open cast mines, where does it end up? It ends up, what do we say, depositing on the, what do we say, their leaves now, right. And then photosynthesis is affected, and that itself stunts the growth of the plant or the crops now. And on top of that, you are going to have what do we say, acidic rain too, and that I guess was a double whammy. Again weakens or kills trees, especially conifers. Again, we are not only talking about conifers, right, makes trees more susceptible to diseases. Again, the issue is that similar to humans, let us say, who live in a relatively more polluted environment, they are relatively more susceptible to, what do we say, attack by viruses or microorganisms now. Similarly, again, trees that are typically not healthy, and whose bark, I guess, or the leaves are being battered by acid rain, they are more susceptible to diseases and what do we say, attacked by insects now. As we looked at it earlier or mentioned earlier, stunts the growth of crops such as, most of the crops that we deal with in India other than broccoli now, right. So, let us move on, and what do we have here? So, aluminum concentration, pH, right, and what do we see as pH increases? Again, this is in a particular place in USA, but again this is universal obviously, right. So, as pH what do we say, decreases, you see that. Again, keep in mind that this is, I guess, a logarithmic scale. You have, what do we say, exponential increase in the concentration of the metals here. That is something that we discussed here. Again, within 60 years, I guess. I am not sure who this is this Mr. Napoleon? Anyway, I will leave that to you. So, again, acid rain, cross boundary pollution. Cross boundary pollution is what do we say, obviously an issue. And in general, we talked about the developing countries releasing a lot of carbon dioxide into the atmosphere, and the poorer countries and the developing countries bearing the brunt of the issue now, right, or the adverse effects. Rather than that, recently, there were not recently, I think 3-4 years ago or even 5 years ago, there was considerable tension between South Korea and China now. It was a considerable diplomatic incident, and the reason was, I guess, as you see, South Korea is along or the near the east coast of China. East coast of China, that is where they have their industrial belt. And again, remarkable levels of particulate matter, and all this was blowing into South Korea, right, this tiny little or relatively tiny country compared to China. And even though the South Koreans themselves were having relatively better and cleaner technologies and were practicing them, all this pollution was or from what do we say, China, which is to the west of South Korea, was blowing towards or over South Korea, and I guess that is the world that we live in now, right. Again, cross boundary pollution, so that is something I wanted to share with you. A large portion of SO2 and NO2 produced in one country obviously is going to be exported to other countries by prevailing surface winds. Again, here we have USA here, I guess, right. And more than half the acid deposition in heavily populated southern Canada. Okay, I guess this is Canada out here, right. And what do we have out here? Southern Canada. Where is this? Where am I? Southern Canada originates from 7 central and upper Midwestern states, and out here, I guess, right. Ohio, Indiana, Illinois, Missouri, and so on, and Tennessee, where coal and oil burning power in industrial plants are concentrated. So, again, as you see, people have to live with it. And here what do we see? We see regions of North America, which includes Canada and America or USA, with low soil alkalinity. Again, alkalinity, why is that important? Alkalinity is a measure of acid neutralizing capacity. Those soils with what do we say, low alkalinity, how have they ended up in such a scenario now? Because they have been exposed over time to considerable levels of acid rain, right. Again, that is something to keep in mind, cross boundary pollution. So, as I mentioned earlier, we have what do we say, burning of fossil fuels and release of particulate matter, and obviously also SO2 and NOx, right, emissions, depositions, and then different effects in acid rain, and then release of metals and oxidized form of what do we say, nitrogen, which again leads to algal bloom and so on and so forth here and such, right. Again, everything is going to come back to these people. I guess here these people are the humans who are overpopulating the earth right now, right. Again, that is something to keep in mind. Coal power plants, SO2 is coal power plants are a significant source of SO2 and other particulate matter, right. And again, what do we have? This is a good graphic, though not from India, because we do not have such data here. Hydrogen ion concentration as pH from measurements made at field laboratories in 2000. So, what do we see? East coast, relatively more industrial areas, I guess, and also here also I believe you have industrial areas, maybe the wind blowing it across too was the reason. So, we see that the pH of all this area is or the soil is relatively less, right. So, again acid rain, more and more acid rain over time, I guess, right. And I guess this is going to affect what do we say, the subsurface systems too. So, something to keep in mind, we are not talking about localized pollution, but pollution of the size of or scale of continents. So, I guess with that I am out of time, and I guess we will look at some more what do we say, questions or problems where we look at not just the carbonate or carbon dioxide what do we say, being in equilibrium with water, but other gases such as sulfur dioxide and so on and so forth, and we will quantitatively look at what is the issue out here, I guess. With that I will end today's session, and thank you for your patience as always.